So, welcome to the sixth session of the for the problem solving on this course. So, I hope you can see this screen. So, that shows this slide. Okay, so let us start. So, yeah, in comparison to the problems that we did in the previous week, so these week's problems are much more easier, and they can be solved uh, in a very short time. So in this session we will be able to cover much more number of problems. So the main concept for this session is to consider some conformal transformation of the form W equal to Fz. So some meromorphic kind of some meromorphic mapping, and looking at how a region in Z plane, say in Z plane, will transform in the W plane under that holomorphic mapping. So that is the main kind of problems, and the concept is very easy. So yeah, okay. So let us start. So please look at this problem statement. Okay, so the problem statements are of this kind. So find the map of a given region under the following transformation, and the transformation will be given like so. This is the generic statement for the problems that will be discussed this week. So for the first one, so this is find the map of this region. So this region is the unit circle in the W plane. Okay, in the W plane. So the region is the unit circle and its interior. So boundary and interior. So we have to find the map of this region under the following bilinear transformation. So okay, so the transformation is of the form W equal to Fz, and Fz is given like this. So Z plus I divided by Z minus I. So okay, so we have to find the corresponding region in the Z plane. Okay, so that will map into that interior and boundary of the unit circle in the W plane. So this first problem, so it can be done in a very shortcut. So let us directly start. So we are already given mod of W less than equal to 1. So just substitute W equal to Fz. So after substitution, so nothing, I just multiplied both sides with mod Z minus I, and then took the square of both sides, and nothing changes because modulus is a positive function, is a positive valued entity. So that is why upon taking the square or upon the multiplication, this less than equal to sign does not change from this line to this line. Okay. And then I have used the formula for modulus of a complex function. So this is for example for mod of Z plus I. So this is so square of the modulus of Z plus I. What is this? So this is Z plus I multiplied by Z bar minus I. So a complex number multiplied by its complex conjugate gives us the square of the modulus of that complex function. So that is why I have used, and then I have multiplied this, and then some terms get cancelled and we are left with this one. So 2i multiplied by Z bar minus Z less than equal to 0. Of course, as you usually recognize, so this is the imaginary part of Z. Okay, not just imaginary part, but it is actually 4 times the imaginary part. So this is actually 4ij less than equal to 0, and that simply implies ij less than equal to 0. So that is that. So we have solved this problem. So in the z plane, the given region is mapped into the region that have imaginary z less than equal to 0. Okay, so that is the answer. And what is this region, imaginary z less than equal to 0? This is the region that includes the entire lower half plane, lower half of the z plane, and also the x-axis, also the real axis. So this is that region. So you see, so how much easier these kind of problems are. So I will now directly move on to the second problem. So that is almost similar. So okay, a little different. So in this problem we were given a region in the W plane, but in the problem 2 we are given a region in the Z plane, and we have to find the map that will correspond to it in the W plane. So find the image of the upper half of the Z plane, or of the Z plane under this bilinear transformation. So exactly similar problem, similar kind of problem, and it can be tackled in the similar way that we have just seen. So let us start. So what is the upper half of the Z plane? So of course it is given. So all the complex number that lie on the upper half plane have imaginary part greater than 0. So the upper half plane is given by this. So imaginary z is greater than 0. Okay. Now let us consider the bilinear transformation. So we are already given this. This is the question. And then I have expressed z in terms of w. So we are given w as a function of fz. Now I am inverting this relation to express z as a function of w, because we are given a restriction on z. So we need to utilize that. So to utilize the restriction that is given on z, so we have to express z as a function of w. So that is why I have inverted the given relation. So that is why I have inverted the given relation. So now we shall directly use the given restriction. So imaginary z is greater than 0. That means same thing, I z bar minus z greater than 0. And then I have simply substituted this z equal to fw. I have simply substituted this one here. And after this substitution, we will of course perform some simplification. So that is that. So okay, yeah. After I have multiplied by I also. So I have multiplied by I the thing that appears inside this square bracket. So that gives us this, and then okay, and then I have added these two terms. That gives us this, and the denominator, which is of course, which is modulus of something, will be a positive quantity. So I have just thrown it out because right hand side is 0, and after simplification we will get this 2 minus 2 w bar greater than 0, and that means mod w is less than 1. So yeah, just simple algebraic manipulation. So the image in the z plane is the interior of the unit circle centered at the origin. So mod w less than 1. So we see the image of the upper half of the z plane is the interior of the unit circle in the w plane under this transformation. So pretty straightforward problems. Now a little different problem. And the problem statement is same, but the approach will be a little different, because this kind of direct approaches cannot be taken all the time. Because you see, I have just, these kind of approaches are more suitable for tackling only the bilinear transformation. But as you know, there are much more general conformal transformation. So bilinear transformation is a very special case, and only the problems involving the bilinear transformation can be treated in this, this this direct way. So this is the most direct way that we have taken in problem 1 and 2. Okay. So now let us look at problem 3. So again, we are given our domain in Z plane. So in this case, we have to find the image of the unit circle mod z equal to 1 that lie in the Z plane under the following transformation. So w equal to 2z plus z square. So you see, this is not a bilinear transformation, but a general conformal transformation that is analytic everywhere. So we have to find the corresponding image in the w plane. So of course, again we start using the usual trick. So whenever we are given a unit circle, what do? We parameterize the unit circle. We parameterize the unit circle by z equal to e to the power I theta. Then we shall simply substitute that parameterization for the in the expression for w. So w is 2z plus z square. So I have simply substituted z equal to e to the power I theta. You will get this, and I have written it explicitly that shows the real part and imaginary part separately. So of course we can write w as u plus iv. That is what we do all the time. So if we write w is u plus iv, then u is the real part and v is the imaginary part. That can be seen directly from here. So we have extracted u and v, the real and imaginary parts of w. So now is the real challenge. So we have to find a curve. So we have to find a curve in the w plane, or equivalently in the uv plane, that is parameterized like 1. So you see, if we consider a curve in the uv plane, so equation 1 represents a parameterization of the curve. Okay. So this is a parameterization of the curve, and to find the equation of a curve that is given in a parameterized form, what do? We look to eliminate the parameter, right? So upon eliminating the parameter, we shall get an equation involving u and v only. So that is what we shall do here. So given the parameterization 1, we have to find the equation of curve that involve u and v only. Okay. So let us start. So here, this kind of elimination problems do not have any general framework, so you have to rely on what you notice, what special properties are given of these functions. You have to rely on these things. Like here you see, you have to rely on observation. So here you see, if you take u square plus v square, so you get a much more simpler function. So u square plus v square gives 5 plus 4 cos theta. You see, meanwhile I have used the cosine addition formula. So cos a plus b equal to something. So I have used that formula here. So u square plus b square is this one. So I have expressed cos theta in terms of u and v. So this is the first step towards elimination. So express a parameter in terms of the variable that you want to express the curve of. So cos theta is given by this, and again there is another observation. U plus 1 is given by 2 cos theta multiplied by 1 plus cos theta. So again you have to rely on observation, and here I have used the half angle formula for cosine. So cos 2 theta is 1 plus 2 cos square theta. I have used that one. So these were the two observations that we made from one. So now we will use that. So as you have guessed by now that now we shall simply substitute cos theta in terms of u and v in this equation. So okay. So u plus 1, so this is u plus 1 is equal to 2 cos theta 1 plus cos theta. So I have simply substituted this. So after simple substitution, the right hand side is this one, and then I have multiplied both sides by 8 and have done some basic algebraic manipulation to get to this equation. So this is our final equation for the curve that is parametrized as 1. So this is the equation. You see, this is in this equation u and v both have degrees 4, and that is not a familiar, so that is not even a conic section. So I think most of you may not be familiar with this kind of curves. So this is called a cardioid. So why is that so? So let me show you some. So yeah, I hope you can see this card. So if you plot that equation that I have just shown, you will get this card. So you see, this is a heart-shaped card. So that is why it is called a cardioid. So I have plotted it using a software. So it is called just type online plot in the Google and you will get this Desmos graphic calculator. So I have plotted using this, and this is the card, so heart-shaped card. So, and this is the v-axis and this is the u-axis. So yes, that is why it is called a cardioid. Okay, so now okay, so enough with this cardioid. So now let us move on to the next problem. So is there any question till now? I don't think so, because these problems are very easy. Not, then let us move on to the next problem. So again, similar kind of statement. So we are given an infinite strip. So infinite strip in the z plane. So this is the y less than y less than half and greater than 1 by 4. This is the strip. This is the rectangular infinite strip. So y is bounded, but of course x is unbounded. X runs from minus infinity to plus infinity. So that is why it is an infinite rectangle. So we have to find the image of this infinite rectangle that is in the z plane under this transformation w equal to 1 by z. So what will be the image of this strip in the w plane? So the most straightforward algorithm is to consider this kind of explicit form for w. So we write w is equal to u plus iv. That is what we have done in the previous problem also, and we shall find u and v by looking at the given conformal transformation. So if w is 1 by z, then u is x by x square plus y square and v is minus y by x square plus y square. So this is the real and imaginary parts of the w, and then now we will have to look to use this constraint on y. So what to do now? So we are given a constraint only on y, but there is but nothing have been said about x. So x can be, thought to be taking any value. So yeah, since there is no restriction of on x, so we have to look to eliminate x from 2. Okay, so from 2 you see u and v are two functions of two variables x and y, and only one of them, namely y, is given some restriction, and x is free to evolve. So since there is no restriction of on x, so we have to eliminate x from 2 and okay, and see what we get. So again we have to rely on our observation. So here u square plus v square is 1 by x square plus y square. Okay, and that gives us from the second equation. So we have found u square plus v square is equal to 1 by x square plus y square, and then we substitute this in the second equation to get y equal to this. So minus v by u square plus v square. See, this has directly lead to an equation of y. So we have expressed y in terms of u and v, and that is what we have to do in this kind of problems. So express x and y. So express the variables that have been restricted in terms of the transformed variables. So we have to express x and y here in terms of u and v, and since there is no restriction on x, so that will not be of much use, but there is some restriction on y, so that will actually be useful for this problem. So y is minus v divided by u square plus v square, and now we use the restriction that is imposed on y. So simple. So again, as you see, simply, since y is less than half but greater than 1 by 4, same thing is applied for this function of u and v, and then I have just, and then simple algebraic manipulation. There is nothing to explain. This leads us to the third line, and then I have simply expressed these two equations in terms of complex variable. So as you recognize, these are two circles, right? So one is w plus 2i having modulus less than 2, and the other is w plus I having modulus greater than 1. So of course these are two circles, and so since this is our region, so one is less than 2 and one is less than 1, So the desired image in the W plane will be the region between these two circles. So this first condition represents the interior of the given circle, and the second condition represents the outside or the exterior of this circle. So of course both of them have to be simultaneously satisfied, so that is why the image in the W plane will be the region that lie between the circle. So again, let us look at the graph. Okay, so here is the plot. So you see the larger circle has radius 2 and the smaller circle has radius 1, and the desired region is the region that lie outside of the smaller circle but inside of the larger circle. So that is the desired region. So that concludes this problem also. So now let us move on to the next problem. So again, similar concept, but what you have been asked to find is a little different. So we are given two straight lines in the z plane. So one is the x-axis, that is y equal to 0, and another is the y-axis, that is x equal to 0. So these are the x-axis and y-axis of the z plane, and we have to consider the images of these two straight lines under this conformal transformation. W is equal to z bar. So let these two curves or these two straight lines are mapped into the curve C1 and C2 respectively in the W plane. So we have to find the angle of intersection between C1 and C2 at W equal to 0. So that is the statement. Now you may think that since in the z plane x-axis and y-axis intersect each other at 90-degree angle, so after doing a conformal transformation, same thing will happen there also. But as you know, that is wrong. So this has been taught in the lecture. So the concept that conformal transformation preserves angle is valid everywhere except the critical points of the transformation. So what are the critical points? So critical points are those where the first derivative of the transformation function vanishes. So here, so at that critical points, a magnification of angles occur. So here you see, here our transformation was W is equal to z square. You see, and if you take first derivative of W, and okay, so W is equal to z square is a what we say entire map. So there is no singularity, so no problem with differentiability. So now let us take the first derivative of W with respect to z, and that will give us 2z. Okay, and 2z is 0 where? 2z is 0 at z equal to 0, and z equal to 0 means W equal to 0. And we have to find the angle of intersection precisely at W equal to 0. So you see, we have to find the angle of intersection at the critical point. So that is why we cannot use the concept that conformal transformation preserves angle. Okay, so we have to go through the long way. So like doing all the calculations from the scratch and then finally conclude what the angle will be. So again, the standard algorithm for these problems. So let W is equal to U plus IV. So we are given W equal to Z square. So that means U is x square minus y square and V is 2xy. Now we'll look at the mappings. So L1. So what is the map of L1? So L1 in the Z plane had y equal to 0. So just simply substitute y equal to 0 in this equation and you will get u equal to x square and v equal to 0. And u equals to x square means, so x square cannot be negative, it's a real number. So that means y have to be greater than or equal to 0 and v is only 0. So that is our curve into which L1 is mapped. So what is this? So v is 0, that immediately tells us that this must be on the real axis. This must be on the real axis of the W plane, but here it is u greater than equal to 0. So that means this is mapped into the right half of the real axis in the W plane. So right half of the real axis including the point 0. So that is why I have called it a ray. So a straight line has no boundary points, so that is the standard definition of straight lines. So straight lines have no boundary points. A segment has 2 boundary points, and a ray has only 1 boundary point. The other end is free. Okay, so this is the definition, and that is why it is a ray, because it has only 1 boundary point at y equal to 0. So this is the ray. And similarly, L2 is mapped into what? So for L2 we had x equal to 0. So just simply substitute this here and you will get u equal to minus y square, and again v is 0. And since u is minus y square, it cannot be positive. So u is less than equal to 0 and v is 0 again. And so this is again on the real line, but this time this is the left half of the real line including the point 0. So again it's a ray because there is one end point. So that's that. So we have, so L1 is mapped into a ray that is being emitted from the origin and extends along the right half of the real axis in W plane, and L2 is mapped into another ray that is being emitted from the origin along the left half of the real axis in W plane. So since as you can intuitively understand, the two curves are being extended in exactly opposite way, right? So will you call them parallel? I don't think so, because if you treat them as two vector quantities, so their direction will be exactly opposite, right? So that is why the angle of intersection will be pi. So had the sense of the direction been same, the angle of intersection would have been 0. But here, as I said, since the two rays are being emitted in two exactly opposite directions, that means the angle of intersection will be pi. And you see these two rays intersect at u equal to 0, because u equal to 0 and v equal to 0 was included in both of these rays. Okay, so clearly they intersect only at w equal to 0. So origin in the W plane, and as I said, the angle of intersection is pi but not 0, because the rays are extending in two opposite directions. So that concludes this problem. So do you have any question regarding that? Okay, so if not, let us go to the next problem. So here we have to first find the bilinear transformation and then look at the map of a given region. So consider a bilinear transformation that maps these 3 points in Z plane to these another 3 points in the W plane. So you see, so a bilinear transformation has 4 complex parameters, right? So this is AZ plus B divided by CZ plus D, and we are given 3 conditions, right? So it maps -1 to -I, 0 to 1, and 1 to I. So now we have to look to find the bilinear transformation by finding a relation between these parameters A, B, C, and D. And there is 3 equations. So there are 4 unknowns A, B, C, D, but from these 3 conditions we can only obtain 3 equations, right? So that means we have 4 unknowns but 3 equations, and that means we cannot completely solve this equation. So one free variable will remain, and we are free to choose what we will treat as the free variable. So let us assume that W is AZ plus B divided by CZ plus D, and then simply substitute Z equal to -1 here, and that is mapped into -I in the W plane. So that gives us this first condition. So -I is B minus A divided by D minus C. Okay. Similarly, if we substitute Z equal to 0, and that should be mapped into W equal to 1, and that gives us 1 equal to B by D. And similarly from the third one, we get I equal to A plus B by C plus D. Okay. So these are the 3 conditions on A, B, C, and D, and if you just do some algebraic manipulation, you will get this equality. So B is equal to D, that is equal to -IA, and that is in turn equal to IC. And so we simply substitute A, C, and D in terms of B. If we do this substitution in W equal to AZ plus B by CZ plus D, we will get this. W is equal to 1 plus IZ divided by 1 minus IZ. So nothing, just simply substitute A, D, and C in terms of B. Or you can choose to do other substitutions also. All of them should give same results, and the result should be W is equal to 1 plus IZ divided by 1 minus IZ. So we have just found the bilinear transformation from the three discrete maps. Now we have to find what is the region in the Z plane that is mapped into the interior of the unit circle in the W plane. Okay, so we have just found the bilinear transformation, and W. So some region in W plane is given, that is the interior of the unit circle, and we have to find which region in Z plane is mapped into this region in the W plane. So again, so this is exactly similar to the problem 1. Yeah, this is exactly similar to the problem 1, right? So there the region was given, bilinear transform was given, and we had to find the corresponding region in the W plane. Similarly, here also the region in the W plane is given, transformation is given, we have to find the corresponding region in the Z plane. So if we proceed exactly similarly as we have done in problem 1, you will get imaginary Z greater than 1. So that means our region, the corresponding region in the Z plane is the upper half of the Z plane. So that solves this problem. So the next problem, so okay, these last two problems are, of course the concept is same, but what we have to find is a little different. Like we are concerned with some families of cards. So earlier we were given a region or a single card, but here we are given a family of cards. So let's see. So first look at the conformal transformation. So our transformation is W is equal to log Z. W equal to log Z is the conformal transformation here, and we have to find the image in the Z plane of the family of straight lines U equal to constant in the W plane. Okay, there is a problem. So in the W plane, we are given some family of straight lines, U is equal to constant, and we have to find the corresponding image in the Z plane under this transformation W equal to log Z. Okay. So let us begin by inverting this transformation. So W is equal to log Z means Z equal to e to the power W. Okay, you could have written W plus 2k pi I, where k is integer also, but that would not have been, that would not have altered the final result, but you can definitely try that. But as I said, the final answer will not change. So I have just simply taken the principal value of the log function. So that is called the principal branch of the log function. So now Z is equal to e to the power W, and if Z is x plus iy, we get this, and Z equal to e to the power W, and W is u plus iv, and that means the real and imaginary parts are given like this. So x is e to the power u cos b, y is e to the power u sin b. So of course, and this looks quite familiar. So if you do this thing, x square plus y square, that will give you e to the power 2u, and that means mod z is equal to e to the power u. And exactly why did we do this? Because we are given some condition on U and we are not given any condition on V. So as we were doing before, so the parameter on which no constraints are given have to be eliminated, and we have to write that parameter in terms of U and V, like in terms of variables in the plane on which you are looking to find a map. So here we are given the constraint on U. So U is constant, is a constraint on U, but that says nothing about V. Okay, so V is free to evolve in any way. So that is why from X and Y here we have to eliminate V, and the easiest way is to do this. X square plus y square equal to e to the power 2u. Okay, that is why we have eliminated V. And this means mod z is equal to e to the power u. So what is this equation? So now, okay, this is some equation, and now if you take u equal to some constant, and that gives mod z equal to e to the power some constant, and that is exactly the equation of a circle, right? A circle centered at z equal to 0 and of radius e to the power u. Remember, now you are treating u as simply as a constant. Okay, and u is simply a constant here. That is why the radius is e to the power u. But we are dealing with a family of straight lines. So that means u is a constant, but a defined constant represents different straight lines in the given family. Okay, so that is what is meant by a family of straight lines. So u is constant, but defined constants represent defined members of the family. So for one particular member of the family, so this is the map of one particular member of the family is this one that I have written. So u is constant, u is some constant, and that is the circle of radius e to the power u. And of course, for some other member, that will be characterized by a defined value of the constant u, will be mapped differently, and for that will again be a circle but with different radius. So suppose that is some u dash, so the radius will be e to the power u dash. So that is why all the members of this family of straight lines will be mapped into circles. So all of them will be mapped into circles, and all of the circles will have center at z equal to 0. But as I say, so the radius will be depending on the constant that will be parameterizing the members of the family, and that means even though all of the circles are centered at z equal to 0, all of them have defined radius, and the radius is given by e to the power u, and u takes defined values. So that means the image of the whole family of the straight line is a family of concentric circles in the z plane, and the concentric circles are all centered around, all centered at z equal to 0. So that is how you have to treat the problems that involve family of some curves. So okay, that is that, and then moving on to the last problem of the session. This is by far the most difficult problem of this session. So again, we are dealing with a family of straight lines in the z plane. Okay, we have to find the image of this family of straight lines in the w plane, and w and z are related by this conformal transformation. Okay, and okay, one thing is that this problem is incorrectly stated in the assignment. So the options that are given in the assignment for this week are, not a single one is correct. So let us find out what is the correct thing. So again, the straightforward algorithm. So z is x plus iy, and w is tan h z by 2, and tan h z by 2 is this thing. So sin h z by 2 divided by cos h z by 2, and that is simplified like e to the power z minus 1 divided by e to the power z plus 1. And then the final line, I have just substituted z equal to x plus iy. Okay, I have substituted that, and well, I have multiplied both numerator and denominator with something to express this function in u plus iv form. So that is nothing but a simple algebra, and you should do that yourself, and that gives us final result. So if w is u plus iv, then from here we can conclude that u is e to the power 2x minus 1 divided by this thing, and v is this thing. So equation 3, that is the real and imaginary part of w. Now again, so we are dealing with a family of straight lines, and the straight lines are characterized by y equal to some constant. So again, we are given some condition on y, but no condition on x. Okay, so that is why we have to again look to eliminate x from 3. So by eliminating x from 3, we will express y as a function of u and v. So let us now look to eliminate x. So from 3, what do we have? So if you divide u by v, so you will get this thing. So again, you have to rely on observations. There is no other trick. So if we divide, so here we see the denominators are same in both cases. So let us divide u by v, and we will get this relation. And also, well, and also v is this. So if we for b, if we divided both numerator and denominator by 2 e to the power x, we get this thing, so sin y. So divide by 2 e to the power x, and you will get this thing, sin y divided by cos y plus cos h x. So these are the two simple relations, and now we will look to eliminate x. So we know sin hx, so definitely we can infer what is cos hx here from here. So let us start. So v is this thing, I have simply written here again, and cos hx is root of 1 plus sin h square x. So this is the relation between cos hx and sin hx. And there is this plus minus sign because negative values are also allowed. Well, actually negative values are not allowed here because x is a real variable, but anyway, that does not change the result. So please ignore the minus sign here. So there will be no negative value. So only For real x, only sin hx can take negative value, but cos hx is always positive. For real x, complex x, it can take negative values also. So please ignore the minus sign here. And okay, so after doing this, I have just substituted sin hx equal to this thing. So you see, I have eliminated x altogether. So I shall express sin hx as a function of y. So that is what I have done, and you get a relation v as a function of y and u. Okay, so x is eliminated. So now the simple thing, so multiply both sides by this denominator and ignore the minus sign, take square and all these things, and you will get this equation. This is the equation of a circle, and I have simply written that in the complex plane. So this is our circle in the W plane. So W plus I cot y, its modulus is mod cosec y. So why mod cosec y? Even though y is real, because cosec y can take negative values. Please remember that y is a real variable. Okay. So this is our circle in the W plane. So this circle has center at minus I cot y and radius mod cosec y. Thus, a straight line, so the family of straight line was y equal to constant. Now let us specifically consider a representative of that. Let us call that straight line y equal to a. So let us now look at the image of y equal to a under this transformation. So the straight line y equal to a will be mapped into a circle centered at W0 is equal to minus I cot a, and will have a radius of mod cosec a, right? Just simply put y equal to a here. So the representative straight line is mapped into this circle. Okay, and of course for defined value of a, we shall have although we will have circles, but all of them will have defined radius as well as defined centers. So all in all, we get family of circles also. Thus the family of straight lines is mapped into the other family of circles, and for defined a, we will get defined circles, as I just said. So here, that is the final answer. And one thing to note is that all of these circles will pass through the points W is equal to plus minus 1. That is a side note, but all of them have to pass through these 2 points. Okay, so yes, so that is the thing. So the family of straight line is mapped into the family of circle with defined radius and defined center, but they have to pass through these 2 points. W is equal to plus minus 1. So that concludes today's session. And so this is the answer, but if you look at the question in the assignment, so none of the options will actually correspond to this conclusion. So all the options are actually wrong. Actually, for the strip was actually minus pi by 2 is greater than is less than y, but pi by 2 was minus pi by 2 was less than y, but pi by 2 was greater than y, and that strip would have corresponded to the whole of the W plane actually, but none options correspond to that. So actually the correct answer would have been the image of that family of straight line is the whole of the W plane. But what to do, I don't know, but the correct answer is this. So, okay, that concludes today's session. If you have any question, please feel free to ask.